All right, so can you guys hear me okay? And you can see my screen, right?
Right.
Okay, cool. All right, so yeah, huge thanks to the organizer who invited me to give this talk. I realized that this is like talk number 9 or something, so I hope you can still learn something new from this talk. Okay, cool. All right, let's get started. So my name is Beer, and the title of this talk is Tightly Connecting Vision and Language. And I wanted to start by kind of unpack this title a little bit, So for the purpose of this talk, I will restrict the definition of vision to images, or basically kind of like snapshots of the world, and language to a piece of text not longer than a few sentences. So an example would be something like this, right? An image, and then one of the texts on this list. Okay, so that's vision and language. Now, what does it mean to tightly connecting the two? Right. So one simple way to define connecting is the ability to retrieve or generate one whole instance of one modality given the other. So this would constitute tasks like image classification, captioning, retrieval, and generation. And given this, you can kind of define tight connection as how informative the text is. Basically, try to enlarge the space of possible text, And here in this example, as you can see, as we go down in the list, right, text becomes more and more informative, right? Things are not very informative because like a lot of things are things, and once you go down, it start to become flowers, and then you start to talk about where those flowers are, what color those flowers are, and the type of these flowers, right? You can also start looking into parts of images or text, and then treat other parts as context, right? In this case, this is kind of like another form of tight connection. We start to take into account the spatial information of the image, right? And this is what people usually mean when they talked about visual grounding. And this would correspond to tasks like object detection, referring expression generation and comprehension, and dense captioning. So you would like to, relate flowers, yellow flowers, dandelions to these boxes, right? And you can throw in, another object here, a green basket as well. And initially achieving tight connection in this spatial sense, requires you to kind of understand context and relationships between objects. So there are tasks that kind of deal with this more directly as well. Visual relationship detection or scene graph generation, right? And then, so basically my point is that, like these are basically kind of the ways you can kind of define tightly connecting vision and language, right? And then it's kind of like what I think of as like generalization of them all, So in visual question answering, given an image in a question, you're supposed to answer it. And you kind of you basically can ask any questions, right? So I guess it means that tight connection between vision and language is needed. Otherwise, how how would you know? Okay, okay. In order to answer what color are the flowers, you have to identify where those are first. All right. So in this talk, I start with this image and text like this, right? And hopefully by the end of this talk, you would feel a bit more like this. Okay, I kind of bring these two together, closer together. And then the goal here is to kind of trying to tightly connect the two and achieve informativeness and controllability, the two definitions that I just described. All right, so we start with informativeness. So most of the thing I talk here is about image captioning, but usually this can be extended to other things. And in image captioning, given an image, you describe it, like two men are talking. And, our team's actually behind, part of the efforts that kind of behind the ability of these Chrome features to actually help and impact blind and visually impaired users. So I just feel like this is like an area where you can actually make an impact. All right, so how do we define informative image captions, right? So I have kind of two main answers right now. First is fine-grainedness. So would you choose to describe that picture with dandelions or flowers, right? How fine-grained this is. And then this compositionality, where once you know the concept of yellow, you can kind of keep adding this thing to a bunch of different objects, right? And it's not just yellow, right? It can be like other things, right? So I can kind of use this compositionality to make things more informative. All right, so how do we make image captions informative? I would argue that a lot of time we should begin with these two.
Hi, Pierre, may I ask a question?
Yeah.
So could you provide a mathematical definition of this informative thing?
Right. So I kind of don't have a precise mathematical definition, but if I were to go back to the previous example, right, where you have like things, if you have the word things, there's a lot of images that kind of correspond to this, right? And now once you say flowers, your subset of images, you kind of narrow down that subset. And once you, say, go down, okay, yellow flowers, flower in the basket, kind of restrict the space of the images that correspond to this, right? So that's kind of one way to look at it. Yeah.
From what you just described, what's the difference between what you just described and the conditional probability? So given one thing, given this, what you just described, like the yellow flowers, and you trying to estimate the probability, what you are looking for, right?
Yeah. I think that's kind of, I agree. Probably that's kind of the way to put it. Yeah, you can think of that as conditional probability. Yeah.
Okay, thanks.
Yeah.
Can I ask a follow-up question? So just in a way, let's say we give you two. One is the caption, the other is the image. Is there any way to sort of just compute the relativeness, the relevance between the two? Or using let's say clip models. That's, I think, the currently easiest way, but that's one practical way, but I think
Right. Yeah, I guess then yeah, so it would be kind of like a joint probability thing instead of conditional probability, I guess. Right. Yeah, I kind of, maybe you all could help me, right? How do we define this informativeness, right? I kind of thought of it as more like this conditional probability, right? Given one thing, how small it is subset of the things or in the other modality you can look at.
Okay, I thought maybe Google has something like a source of your own of doing that, but yeah.
Yeah, we talked about that a little bit too later in the talk. Okay, all right, so okay, let me get back to this question, right? How do we make captions informative, right? I propose that we do this two-step first. Actually, this kind of apply to a lot of machine learning models, but I guess more specifically to image captioning. So in this context, I talked about image captioning, right? So step one, you should look at training data, and ask whether captions informative, right? And then you look at what you provide to the models, right, as input, and ask if these input signals informative. Okay. So let's go to let's talk about step one really quickly. So this is basically training data, right? And the most popular training data for image captioning, as most of you may know, is Microsoft Coco, right? MS Coco. I call this Coco captions, and it's it's like 120K Coco images, 5 caption each. It's human curated. So you ask humans to describe important parts. It has to be kind of long, right? And it's very good. You have 5 captions per image. It's very fluent. Image and text are related very well, right? And you have all these other annotations on Coco, right? That you kind of leverage for image captions, right? The bad thing is this is okay. 120K images kind of like small scale. I mean, by today's standard, right? And given that, probably you won't get something that kind of diverse enough visually, and as a result, you won't have diverse enough linguistically captions as well. Right. So just to kind of, illustrate this, right? There's this data set called no caps. And then there's this Coco has this 80 classes. So, docs, bench, and then open images, 600 classes. So things like goat, artichoke, accordion, dolphin, waffle balloons, you won't find Coco. Right. So it's not, probably you want dolphins and waffles there, right? It's pretty kind of common objects. And basically this Coco objects kind of cover the head of the distribution, not so much the tail of the, distribution of object categories, right? When you compare Coco and OID. Right. Then once you train image captioning model on Coco and ask human to say, okay, whether it's excellent, good, bad, embarrassing, right? So of course, if you Coco test set in domain evaluation, it's excellent, at 51, okay, more than half the time, right? And this is 2016 paper, so probably you get something even better these days, right? But once you go to Instagram, most of the time, once you go out of your training dataset domain, things start to go wrong. One alternative to COCO is conceptual captions. Right? It's 3.3 million clean, hypernemized image alt text that is automatically collected from the web. So just to show you some example, these images, right? And you probably, this is our images that you probably want to see in COCO, especially this cartoon illustration, right? And these are some example captions, right? It's look pretty good. So, I mean, I should pick this a little bit, right? Yeah, but yeah, no, usually it's like a little bit, okay, it's noisier, right? Because not human curated, right? You look at the image, okay, you look at the images and, okay, oh, this is very diverse because, there's like outdoor multiple images, black and white, there's like abstract thing, close up of fingers, right? So this looks like a pretty diverse set of images, right? To collect this data set, start from image and alt text, you go through image filtering, text filtering, image text filtering, and then text transformation. So, and then in the end, you get, this picture of Demi Lovato as pop rock artist wearing a black gown and sandals at awards, right? So let's go to this pipeline, In the end, when you compare this to, you get a like orders of magnitude larger data set, right? It's silver data, not gold, right? But it's much larger. And then also more diverse, right? All right, if you compare COCO train and CC12M train models, predictions, right? Maybe just look at the last column, right? Obviously we want something that can say this is like a cartoon or illustration or something, right? Not a picture of fish on the side of a car, right? So, and again, you can do human evaluation. This time is on Flickr test set, and this 1 + 2 + 3 + is basically the number of people who say captions are good, right? And as you can see, if you train on CC12M, which is conceptual here, models tend to perform better in a while. All right, so I just kind of talked about this training data really quickly, right? So let's say, since CC12M seems to be kind of larger scale, more diverse, and output captions seems to be more informative. So I kind of, okay, let's focus on CC12M. Okay. Now, okay, step 2, look at the model outputs. Okay. So I trained CC12M model on state-of-the-art image captioning model, and it gives me a woman, this picture. A woman walks through the streets, right? Very bad, right? Even though you train on CC12M, right? And okay, let's try to understand why this happens, right? Usually, image captioning model would consist of these two parts: visual feature extractors and caption generator. I don't know, going forward, this is going to be like one big thing. You operate everything from pixels. But I think right now, you kind of still have visual feature extractor, right? And what this means is usually in the context of image captioning, this is object detector. And this task is basically, okay, here's like a popular object detector called Faster RCNN. And you run, okay, I run object detect this Faster RCNN on this image, right? It draw boxes and tell me what these boxes are. And you get something like orange dress, woman, man, orange skirt, white house, woman, right? So now once you see this, it's not very surprising anymore that you get that kind of caption, right? So it seems something's wrong with the we can kind of we should be able to kind of optimize this input signals to the caption generator, right? The problem here is basically these visual features are wrong or not fine-grained enough, right? So instead of house, maybe you can say something more. This is not just like, house, right? Okay, so when, so input signal are not informative. So I guess this is kind of like a meta thing, right? Then step 2.1, you look at the training data of this feature extractor, right? And usually people use ImageNet pre-trained backbones and fine-tune on object detection data set like visual genome. And you have like 1,000 or close to 2,000 object categories and 400 attributes. So this is not a lot.
May I ask you a question about the previous slides?
Yeah.
So this means the vocabulary for the object detection in COCO is not big enough to be informative.
Yes, exactly.
Okay.
Exactly.
Okay. Thank you.
Yeah. All right, cool. So yeah, 100 object categories, okay, exactly what you just said, right? The vocab size is kind of small, image classification, object detection here, right? How do we fix this, right? Because we want to fix from the data, right? It's fixing from the data. So one way is you build a new object detection data sets that can provide richer vocabularies that cover this image objects for image captioning models, right? So this would involve you ask people to draw boxes and assign kind of like fine-grained labels, among this larger space of vocab, words that you define, right? And then you train an object detector on this data set. But as you can imagine, right, this is very expensive, right? So let's look at this again. You can kind of see that boxes are okay. It's just that labels are not very good, right? So we come up with a better way, So we reuse boxes, and let's try to kind of, make sure that these features are do not correspond to orange dress or woman, right? It's correspond to something that is correct to more fine-grained. So we're gonna try to featureize this box well. And this is where I bring in this concept of outer fine-grained semantic labels. You kind of want to increase this, fine-grainedness of your labels from category level like bridge to fine-grained level like steel red bridge to instant level of golden gate bridge, right? And luckily, we have internal data that very, very fine-grained at the image level, right? Here we're not talking about like object detection, right? But we're gonna pick each box and featureize them well, right? So the details of this doesn't matter, right? But what's matter is like how many classes do you have here, right? And this is 40 million classes, right? And you can kind of subsample into, you have to do some subsampling of these classes. I call this graph rice, so you can kind of check the paper as well for kind of details, So here then what I mean by feature IDs box as well is gonna leverage large amount of image level data. Right, and we have an EMNOP paper 2 years ago that's kind of basically this, get boxes, do out of fine-grained featureization. Do we get better visual features? Okay, I want to talk about this caption generator really quickly, just get it out of the way.
Pierre, before, may I ask you a question about the previous slides? This one. So you basically talk about the in the ultra fine-grained features. That means you significantly increase the dimensions for the number of the classes. So you have extremely more classes, right?
Right.
So in that sense, you increase the number of classes to increase the featureization.
Right.
So is that, so I'm trying to understand what this featureization means. Is this means because before your feature only related to the 80 words, but now your feature related to 4,000 or 100,000 words. So that means your feature is more related to the vocabulary in the NLP, in the
Correct.
text.
Right.
Right.
Exactly.
So,
yes.
Okay, so you introduce the number of the classes, trying to introduce the relationship to the more number of the text, right?
Right. Right.
Okay. Thank you.
These continuous vectors that you would provide, right? Yeah, exactly what you said. Yeah, it would align better. It would be tightly connected to the actual language, which is caption, right? Yeah.
Yeah, I'm trying to understand from the opposite way. So which means rather than related to more number of the text, so in visual feature itself, does this object has more relationship with other objects in the visual space rather than in the text space?
What do you mean? What do you mean by that? The visual, visual features have what relationship? Sorry.
So, for example, before, let's say you have a person, you have another person, and they wear different clothes at different positions, place, and before, you define this is a person, so they only correlated to each other through the person, right?
Right.
So later on, you define more text. So let's say this person related to maybe a tree, and related to some machines, and related to a cell phone, etc. You related to more things, and those more things, of course, give you more attributes for that object, and will be good for the downstream VL task.
Right.
But I'm thinking only for the vision task itself. So this one may introduce some better representation for that person. It also may introduce some noise for that person. So from that point of view, I want to understand, let's say, if we have such kind of the representation, let's say if we focus on the vision, that's the object detection purely, and this kind of thing introduce more representation power or introduce more noise.
Yeah. I guess. Yeah, that's kind of a good question. I guess, right? How if you work on object detection, you kind of have to exactly define these vocabularies, right? And yeah, there's a trade-off, specificity and noise, right? But yeah, for image captioning, you kind of you hope that caption generator would do something, right? You should be able to kind of you give the input signals that are more fine-grained but a little bit noisy. It will be able to make use of those than something that all person are the same, right? Then
Right.
Yeah. So for vision and language, I would say this is kind of like it's okay to kind of be a little more noisy.
Okay.
Yeah.
Thanks.
All right. Yeah, I just want to kind of talk about this caption generator really quickly, right? So this is basically just transformer encoder decoder model. If you know, like machine translation, right? You stack a bunch of transformers layers, and then you translate one language to another. So this would be from text to text. And then for image captioning, you can just kind of replace the input with a bunch of image features, right? And in this case, I'm gonna mainly compare FRCNN, which is those woman orange skirt that you see from faster RCNN, and Ultra, which is the thing I refeaturized, right? With out of grain semantic labels, right? There are other things that, kind of fix the same, okay? And now let's look at the output of this, right? The ground truth in CC12M here is monks clean a garden at a temple. So before you see a woman walks to the street, right? Now we get monks walking in front of the temple. So get monks and temple, right? But not walking, right? So, okay, at least better, right? Another example, black sesame seeds, instead of dry flowers, we say black chia seeds. Very close. Car and tree ornament this heart of mine. So, okay, ground truth is not too perfect, I guess. But yeah, digital art select for the shop. This is kind of, I don't know what this is. But then Christmas tree in a toy car. Probably not in, right? But it's pretty good. Once we do this featureization, out of fine grain featureization, right? So, right, I can go on about, okay, how informative words appear, right? Once you use this ultra approach, right? And before, it would be really hard to kind of say, okay, this is lollipop from Red Frisbee, or this is algae from blues, like a bunch of blue skies and leaves, right? It would be really hard. Turns out you can kind of apply this idea to VQA as well, right? Another vision and language task. And it's really useful in the case of number and author question types, where you may want something that is a little bit more fine-grained, right? So for here, you go, what is this? Here, you actually need to know, okay, you want to go like fine-grained, right? You just don't want to just say this like bottle or something. So instead of beer, yeah, you say this is barbecue sauce, right? So conclusion here is that out of fine grain visual features leads to informative image captioning and VQA, right? Okay, someone asked about this, like if you want to do object detection, right? This is probably the paper you can check. This is basically, we want to work on long tail object detection, but how to take, okay, we work on object detection and how to take care of the long tail, right? By leveraging the, again, image level labels, which we call object centric here. And we come up with a very simple idea, okay, based on this mosaicing. Okay, the details on this kind of have to check the paper. But yeah, I encourage you to kind of check this paper out, which kind of recently got accepted to ICCV, Right, so I talked about how do we make captions informative using these two steps, right? But as you may imagine, once I don't know, people talked about bird, and there's like a lot of vision and language bird and so on, right? These days, you kind of have to add step 0, right? Which is you have to look at pre-training data as well, right? You cannot just, okay, no one trained from scratch these days, right? And before 2021, these are the things people kind of use to pre-train, you know, SPU captions, COCO captions, PKV2. And CC3M is actually a very, very popular pre-training data set for vision and language, right? What we introduced, here I talked about how we use CC3M as target image captioning task before, right? So it's not gonna be our pre-training data, right? So what we have is kind of something larger, which, you know, this is like a CVPR paper. We call it Conceptual 12M or CC12M. And we kind of try to decide this for vision and language pre-training. So we do not care too much whether this is kind of like a good captions or not, right? But similar, we use like kind of like a similar data collection process. You know, we start from alt text, but then we trade precision for recall, right? So as you can see, you know, here you have like sumo and mangosteen and, you know, like a bunch of hashtag about jellyfish, right? So as you can see, it's not as clean as CC3M, right? So if you remember, this is a pipeline I use for CC3M data collection. Now in CC12M, I'm gonna, you know, relax a lot of image filtering, text filtering part. You know, I keep image text filtering and then text transformation as well. You know, I don't do a lot of things that CC3M did. And then we also did this person thing, you know, okay, I think this is Donald Trump, but yeah, it was replaced with person, you know. So yeah, this is for privacy. And then if you compare, you take no caps categories, again, you compare the objects, you can see that, okay, CC3M actually cover these objects in the tail more, this out of domain classes more than CC3M. You know. Now, if I pre-train on CC12M, right, and then test on CC3M image captioning, I get something like 30, 40, you know. If I train from scratch, I get something around 93.7, right? But then once you fine tune CC12M pre-trained model to be so that the language is similar, similar style to CC3M, you can improve the results from training from scratch significantly. And okay, I don't know how many of you are familiar with no caps benchmark, but it's basically just a test only image captioning data set where you train or fine tune on COCO and then you test it on no caps, right? And we kind of used this CC12M and CC3M as pre-training data and fine tune on COCO. And we were at the top of this leaderboard for a while until WinVL came to life. Okay, so both of these are from Microsoft. Okay, number one and number three are both from Microsoft. Number three, I think, is called Vivo. You know, so right. So this is no caps leaderboard. Turns out this is okay. All three of us, you know, beat humans in this task. You know, this entire data set. You know, on this automatic evaluation, and we are doing really, but we are doing really well on the out of domain part of no caps. You know, even though right now I can kind of not compete with humans for this particular out of domain subset. Right? Let's check at this a little bit. So I guess, you know, the most important part is what is COCO caption, right? So here it's a group of people. And then you see CC12M, after you fine tune on COCO, you get sumo wrestlers in this case, right? So people to sumo wrestlers, something that's more informative, right? And then here COCO caption says something that's completely wrong because this is not microphone. And CC12M pre-training changed this to SOR, whereas CC12M correctly pre-train and fine-tune on Coco correctly say this is bagpipes. And yeah.
Hi, Beer. Can I ask a question?
Yeah.
So this is Peng Chuan. I want to, how do you do the pre-training on this CC12M? So it's like standard mass language model pre-training, or in fact it's just use image captioning as a pre-training task?
Right. Yeah, that's a good question. I kind of missed telling you that this is basically just image captioning, both pre-training and fine-tuning. So you do image captioning on pre-training data, and then you image captioning on Coco caption. No masking or anything. We actually try a lot of other tricks that this masking, right? But we found out that nothing can beat image captioning. Objective. Okay. So okay.
The other question, this is just a discussion. There's no other purpose. So for the no caps leaderboard, I think for the standard leaderboard, we are not allowed to use extra caption data to do training. We can use extra, for example, OD data or something, but we are not allowed to use caption data.
Right. Okay, we kind of interpret the rules as human curated captions,
Okay.
But yeah, I think that's kind of arguable whether we should kind of separate these two leaderboards. Yeah, but yeah,
okay,
you can Okay. Okay. Skateboard to motorcycle to Segway. Right. So it seems that please check this out. Conceptual 12M. And I kind of want to mention this really quickly. In 2021, there's a lot of other things you can explore, right? Probably not clip and align, which is like much bigger, but it's not publicly released, but probably you may have something on your own, right? But yeah, there's a lot of other things, red caps and wit English here, a lot of image text data. So I'm done with informativeness, and I have about 15 minutes. So I try to go to the rest of the talk really quickly. Any quick question at this point? Okay, cool. Okay, let me go through it. Okay, so controllability. So motivating example, right? Let's say I don't want to, talk. Okay, I just want to understand what this is, right? Okay, you can draw a box in this image, and then image captioning model should be able to produce you a green clock nearby the street, right? And then you can give the model a bunch of draw a bunch of boxes, and then it should tell you in order 2 men are talking, behind them there's a green clock. This is what I meant by control image captioning, right? And this is like, when people cannot see very well, this is usually the problem, right? What they want to understand, okay, maybe it's this area that I want to understand more, right? You want to be able to control it a little bit, right? So the question is, what should I talk about and in what order, right? And here, the problem is captions may not satisfy each user's spatial and temporal preferences, right? And our work, Localized Narratives in ECCV 2020, the data we basically introduce efficient data collection method for visual grounding that will allow you to do controllability at scale. And it's on Coco, Flickr, 80K, 20K open images, a subset of open images, right? So this data collection effort was led by Jordi and his team in Zurich. So let me show you really quickly how this works. In
the front portion of the picture, we can see a dried grass area with the dried twigs. There is a woman standing wearing a
Okay, I don't know how the sound works. I hope okay, everybody can hear, but basically we ask the annotator to kind of, move the mouse around, describe this image, right? And then the minute, okay, so you have this, and then once you talked about clouds, kind of, okay, this is this area, right? You move the mouse around this area. So you kind of get visual grounding really quickly, right? So just a little bit of detail, okay. So things like this, right? Shapes, spectacles, open land with some grass on it. This correspond to the mouth trace. And okay, the text means there, you use the mouse to underline. The annotator use the mouse to underline that, right? And the way this works, okay, actually I'm gonna skip this part, but I just wanna tell you that in the end, we're gonna get text, and where for each token, you can kind of tell which regions in the image that these tokens correspond to, right? And basically, this is a very, very scalable way to tightly connect vision and language, spatially, yeah, like visual ground in a visual grounding sense, right?
Beer, can I ask one question? I thought that in the connection part, there's no keyboard type. A dog runs on the snow. There's only voice and the mouse tracers. So
there is.
But from this picture, it seems that the annotator also types something.
Right. After they speak, they kind of type something, right? Yeah. So yeah, okay. I wouldn't claim this is faster than standard image captioning, right? But if you want to get visual grounding, this is pretty fast.
Mm-hmm.
Yeah. Okay, you can do a lot of tasks on this. Given speech, mouth traces, text, and image. Obviously you can do image captioning, control image captioning using the mouth trace as a control signals. You can inverse this, text to image generation and the control version. You can involve speech, and then you do grounded speech transcription. Okay, let me talk about application we show in this localized narrative paper. Control image captioning. And really quickly, what we did is basically just turn these mouth traces into a sequence of boxes. Just in a similar way I show in when I describe control image captioning, right? And here's the results. If you just, okay, this is basically trained on localized narrative COCO, right? And standard image captioning model would say there is a file hierarchy and this is road. But once you start to control it, so there's like this color and time, right? So in the input 2, you talked about the platform and this yellow color thing first, whereas in input 3, you talked about car first, right? So you can use this, with this data set, you can kind of train a control captioning model. Okay, I'm gonna skip more these examples because we run out of time. But the message is that not only that, you kind of, you got to get more detailed captions also, right? Maybe the user kind of want to know more about donuts, or there's like a sign in front of this machine, and what is in the background, and so on. In the paper, you could kind of had also like a preliminary results on controlled text to image generation that was enabled by localized narratives. So you say both on an empty canvas and you move the mouth trace, right? And then you get both. Just a bad board, I guess. It's preliminary, right? Then you say water. You can see that now board is changing, right? It's not the same as before. And then it started, I want person on this board, and I want an umbrella. No, so this is the thing. It was enabled by localized narratives dataset. right? A mountain. And there are other examples. Can take a look at that in a paper, And the quality of these images are not too good. I say it's not realistic. And there's like people who are actually try to improve this. There's a lot of other related work that use localized narrative and then optimize the quality of this image synthesis. All right. The last thing I want to talk about is instead of generation, we can also do retrieval. And this is ICCV 2021 paper based on localized narrative as well. Okay. So this is localized narrative, right? You have image, mouth trace, and text. And then similar thing you did with the generation, right? If the user wants something in a database, the user can kind of speak and draw something on this empty canvas, right? And then you have this synchronized thing where, okay, what's the target image, right? So we call this what plus where image retrieval, And if you actually think about it, this is like a this is a good query modality, right? Because if you want something that is more specific, so this Bob wants this picture in the top left, right? But if he use a text like in A, he would get something that is incorrect. That's not what he wants. But then, if he kind of want to use text to kind of keep refining text in A, start to be more in detail, image retrieval system would be really confusing. And Bob has to use a lot of words, right? It's kind of inconvenient. And if Bob say a horse in a city or clothing a bike and a car, why he is like draw these traces in empty canvas, but it's like a very, very convenient modality for pointing to the where, right? And basically, this is what we do. It's what we propose. This new query modality. You get both of ease of pointing to the where and fine-grainedness of the what using language. Okay, let me skip the model part. And jump to the results. This is on Flickr, 30K localized narrative datasets, and we usually call at K as the standard metric for image retrieval, and we also play with both pre-training and no pre-training scenario. And as you can see, we compare text versus text plus trace, right? And here you get much better target images when you have this trace to control what target images that the user wants, right? Significantly improve the recall at K and MAP as well. So it's kind of the same trend. This is, okay, you get even better improvement once you evaluate this Flickr train model on out of domain ADE, K20K, and Coco. Okay. Here is one thing I want to mention here is that CC seems to be better at this fine-grainedness of things, because it's kind of collect automatically and people say different things from the web. Whereas localized narrative, again, it's come from people, but then you get this visual grounding, right? So it seems that this data set are complementary in a way, if you look at text only, right? And then localized narrative comes with trace also. You can kind of use that for pre-training. And for this task, it seems that, just using OID localized narratives for text plus trace query modality works best, whereas you should do both CC12M and localized narrative for the text query modality, text only query modality. Okay, here's an example. Okay, look at a tennis, right? Tennis should be around here at the top right, right? And then if you just see the same text, then you get the wrong image. Whereas here, with the mount trace, it kind of refine that. Okay, I want tennis ball right here, tennis racket right here, and then it's correct. Okay, check this out. This is localized narratives. In conclusion, I have talked about ways to tightly connect image and text, and I have talked about better signals by leveraging existing large-scale data. I've talked about new data set, CC12M, and localized narratives. And I talked about new applications, mostly enabled by localized narrative, right? Control image captioning and control image generation and control image retrieval. Right? So, yeah, hopefully you're convinced that, they are image and tech are brought closer together in a sense of informativeness and controllability.
Thank
These
you.
are the papers in this talk, and want to acknowledge all my co-authors. And yeah, thank you so much for coming.
Thank you, Bill, for the very nice talk. Let's thank our speaker. And if you have any questions, please feel free to ask the speaker.
Bill, so in fact, I have a question about the grounding datasets, the local narratives. Traditionally, grounding grounding annotation is boxes like what we have in Flickr certificate entities. This kind of grounding annotation, but now in local narratives, we have traces as grounding annotation. I want to know that how do you compare this kind of two kinds of grounding annotations, and also have you in your applications, have you ever tried to convert the traces to the traditional box grounding annotation, or in fact you think that okay, the trace annotation is already fun for the applications you want to do?
Right. Okay. For trace versus boxes, I think I'm kind of not sure. It's kind of unclear, right? Which one would be better? But in our experiments, actually, we do turn all the traces, except for image generation. We do turn all the traces into a series of what I call trace boxes, and basically, what you do is basically just kind of draw boxes around chunks of traces. So in our experiments, it's actually visual grounding in that original sense that you understand. But yeah, I feel like there's like more to be done in terms of understanding what's this like media, like if you want to do visual grounding, should you have boxes or you should have something else?
Oh, yes, thanks. So I want to know whether you have, I didn't check it out, but I want to know whether you have released open source the kind of script or tools that converts this traces into trace boxes.
No, we didn't. I don't think so. But yeah, I'd be happy to give you some pointer on that. Yeah.
Okay.
This is not something complicated at all, I have to say. Yeah.
Yeah, I think there's some heuristic rule there to convert. For example, kind of where is the boundary? This kind of thing. I think a little tricky. Yeah. Thanks.
Any more questions?
Hi, Beer. I have another question I want to ask you. So I thank you for the presentation. This is a really good presentation. And so I like the picture you draw, the image sequence with the text. But from your presentation, I feel essentially it's not this two shake hands. You essentially you turn the images into a bunch of words, into a bunch of text, and then purely leverage the power of the NLP to do the rest of the modeling. So for example, so once you have more number of classes for the objects, basically you trying to push more attributes on each objects, right? So before a person is a person, but now each person has a multiple words, a bag of words to represent each person. So in that sense, you turn the image into a more texts. Is this correct?
No, okay, actually, probably I wasn't clear in the talk. Okay, this wasn't very clear in the talk. I still used this continuous visual features vectors as before, except that during like the pre-training phase, instead of ImageNet or visual genome, right? You have like a much bigger vocabularies, right? So in the end, the input to the image captioning model is still this continuous feature vectors, but you are right that these continuous feature vectors are correspond. But the features for, I say, like monks wouldn't be the same for all the images, right? That contain monks.
I agree. This in a continuous space, but you're trying to push those attributes in one vector. This one vector will essentially, in an implicit way, a bag of words.
Right.
So this give you, and then you can relate it to the text, and to leverage the NLP and model the relationship between all those words, and you get the final result. So this, I can give you a very extreme case.
Yeah.
A very extreme case is given an image, I convert the object representation, class, and four corner coordinates into a text. Okay, so given an image, I have person at this box, 4 coordinates, and bicycle, 4 coordinates, and bird in coordinates. So I can generate a text like this. But if you can learn the image and this kind of text, you solve the object detection, right? But this kind of thing is not there. I don't think currently any VLP models can solve this, because if you solve this, you solve the object detection. So that means there's what, so that means because this one you cannot, because the coordinates and the classes, you cannot represent this in terms of relationship between the words, because there is geometry over there, right?
Right.
So in that sense, is currently you the image and text shake hands in terms of the word relationship, but not in terms of this geometry.
Well, you also have the global features, right? So maybe you can make use of that, right? In terms.
But could you solve the extreme case I just mentioned? The text is purely object label and object coordinates. This is the label per image, and give you this data set. That's the COCO. Every image, you have a vector of the classes and 4 coordinates of the bounding box. Give you this image and text. Could you model it and give me a perfect object detector?
Yeah, I'm kind of not sure I understand your setting exactly.
So let's say I give you an image, and this image, there is a person in it. Okay, this person in the, and this person has 4 coordinates, top, bottom, left, and right. And the text, the caption of this image is person.
Right.
Left number, right number, coordinates. Let's say 100, 200, maybe top is 50, and bottom is 250. This is the text. 5 words, 1 word, 4 numbers. This is the caption for this image. And for all of the images, it's like this. Could you solve this problem?
So I don't see how this is related to the the fine grained thing. So you're trying to turn object detection into captioning, right?
Exactly.
Right.
So if this not cannot solve, that means there is one type of the caption you can solve, but the other type of caption you cannot solve. So so there must be some condition over there to show if you satisfy this condition and this image caption stuff works. And otherwise, like the extreme case of the object detection text, this one cannot be solved. So I'm trying to understand what is the boundary, what is the condition, and the image caption works, and in which condition it doesn't work.
Yeah, I mean, yeah, thanks for raising a theory question. Right. Okay.
So my understanding from what you just described is because in this case, in the scenario you just described, you can turn an image into a bunch of words, and those words are meaningful in terms of the natural language. And you add the properties, you keep adding the properties to each object, and they may have some relationship, which is also can be represented by the language. And in that sense, this is not a mathematical definition, but this shows in this kind of situation, and this the image and the text can easily shake hands. And in the object detection case, and that image and text cannot be easily shake hands.
Yeah.
Hey, Pension, I want to say, if you're interested, tomorrow we still have slots for one-on-one with Bill.
Okay,
so,
cool.
Right, just sign up on the Excel, and hope you will enjoy the one-on-one with Bill.
Okay, cool. Thank you.
Right. Any more questions? If not, we may close the meeting, and I think everyone enjoyed the presentation. And Bill, I think tomorrow you might already have maybe 2 sign up for the one-on-one, and hope you will enjoy it. And if you have any questions, please feel free to reach out to me.
Yeah, thank you so much, the organizer, and thanks everyone.
Thank you.